Reality, captured in user-friendly symbols and processed for understanding. The Idea Channel.
Okay, Mark, one of the most fascinating questions in cosmology today is what is this stuff, this 90%, maybe 99% of the stuff in the universe that we think is around but don't see, this problem of dark matter.
This problem of the dark matter is a fascinating development that has been known for 50 years. Astronomers have been saying for more than 50 years that there seems to be dark matter in these clusters of galaxies. There's dark matter in the outer regions of normal galaxies. And now the idea that this dark matter dominates the total mass density of the universe, perhaps accounting for 90 or 99%, is what many people call the ultimate Copernican revolution, that we're not even made of the dominant material which comprises the universe. The Copernican revolution, of course, refers to the notion, first really argued strongly by Copernicus 400 years ago, that the Earth is not the center of the universe. The stars don't revolve around the Earth. The sun doesn't revolve around the Earth. It's the other way around. The Earth revolves around the sun. Now we know the sun is just a very minuscule speck on the outskirts of one galaxy, and there are millions and millions of galaxies that we can see out there. So we are clearly not the center of our universe. But we used to think that we were made of the most dominant stuff of the universe. Our atoms were the dominant stuff, the hydrogen, the helium, the oxygen, etc.
So how do we know? Because, okay, first maybe there are two questions. How do we know that there is something dark if we cannot see it?
That's the first question. How do we know, what is the evidence that there's dark matter at all? The evidence has to come through its gravitational effects. We use the laws of Newtonian mechanics that have been around for 300 years. Those are the laws that govern the orbit of planets around our sun.
So we see stuff going around spiral galaxies?
We see stuff going around spiral galaxies. It turns out that we can measure the light in the galaxies, and we have a fair estimate of the mass of a star.
So, and we can measure the velocity of these clouds?
That's right. We can see the velocity of clouds, and we know, for example, in the solar system, that we are orbiting the sun at 30 kilometers a second, and if we were 4 times further away from the sun than we are, we would be orbiting at half that speed, 15 kilometers a second. This is known as Kepler's law, that and just as a simple relationship of Newtonian mechanics, that if you're away from a star, your orbital velocity falls as the square root of the distance. But in a galaxy, it's a more complicated situation because the mass is not concentrated in a central star. It's spread out over all the light of the galaxies.
Well, it's basically the equilibrium between centrifugal force and centripetal force,
and the gravitating mass.
Yeah.
And when we do that calculation, we would say that the rotation of the outer regions of the galaxy should be falling with distance from the center of the galaxy. But they never fall with distance. All the galaxies that we've observed, and it's quite a few now, many, many dozens, every one of these galaxies has a rotation curve, that is to say rotational velocity as a function of distance from the center, that is flat with distance, as though there were a dark matter component in that galaxy whose density was declining with distance, such that the total mass of the galaxy is not converging. As you add up bigger and bigger shells, the mass continues to grow linearly with distance.
Even though we cannot see any stars.
We can see nothing. It's clear it's not stars, it's clear it's not ordinary gas, it's not ordinary, it's something that is very highly invisible. It doesn't appear to be ordinary matter.
So this seems to be true for our own galaxy, this seems to be true from many of the spiral galaxies that we can measure.
That's right. On any system that the astronomers try to measure mass on scales larger than, say, the distance of us to the center of a galaxy, 20,000 light years, any system that large or larger always seems to be dominated by dark matter.
Even the elliptical galaxies seems to have also some dark matter. We can measure globular clusters, smaller.
That's right, and we can measure the confinement of their hot plasma, which seems to be confined in a way that's inexplicable unless there's dark matter.
And we see this hot plasma because of the X-rays that they emit. And,
that's right. So, and we see in clusters of galaxies, we see two evidences, two different lines of evidence to suggest dark matter. In Zwicky, Fritz Zwicky, a famous astronomer 50 years ago, said...
That was the first one to
talk about it, well before its time. He said that the galaxies in the Coma cluster of galaxies, a very rich agglomeration of 1,000 galaxies.
Yes, there's 1,000 galaxies.
1,000 galaxies or so are moving around much too fast to be held together by their own self-gravitation, because he could calculate the amount of gravitational attraction of all the material there, assuming the stars made up the total mass.
We're similar to the sun. And
it was wrong by a factor of 50. I mean, as though 50 times more mass were needed than appeared to be present in the stars. I mean, this is a fairly astounding discrepancy. And he said, I don't understand why this cluster exists. It must have some unseen form of matter. And now the evidence is confirmed in many different experiments. There's unseen matter. Now, but your question of...
But you spoke about a second evidence, which...
Oh, the second evidence, right. Well, that's called a virial analysis of the galaxies orbiting in the cluster. The other evidence is the nature of the X-ray emission. Again, this hot plasma, which is confined in the cluster, emits radiation, and by mapping its density distribution and estimating its temperature distribution with some simple equations, we can show this provides an unambiguous estimate of the mass. Again, coming up with a very high mass, much higher than is given by the stars.
I think there is a further, actually, piece of evidence in the clusters of galaxies.
Oh, I guess there's the lensing.
The lensing.
Right.
Yes, the arclets, the fact that we can measure the mass of the clusters by the amount of bending that it gives on the galaxies which are in the background. And there again we obtain very similar results than with the velocities of the galaxies and the temperature of the X-ray gas.
Now, this question, though, about the nature of the dark matter, I guess we should think about what is the argument that says that the dark matter can't be rocks or something that we just too small to shine, but just ordinary material that's compressed, like snowballs or something of that sort. Why do we think it's not the stuff that we're made of?
We're not sure. Okay, that's really maybe the first answer. But we have a pretty good idea of how many protons and neutrons there are in the universe. This is so-called nucleosynthesis argument. One of the major confirmation of this general picture of the hot Big Bang is that we can compute the amount not only of hydrogen but the ratio between the hydrogen and helium, the deuterium, the lithium-7, which has been produced in the Big Bang, and we have only one parameter to fit a large number of data, and this parameter is just the amount of baryons and the amount of protons and neutrons. And if the best fit to all the data gives 5%, something like that, 5% of the critical density is in baryons. The critical density is this density of the universe where it just expands forever and just coast at infinity. If it was slightly more massive, it would recollapse.
Slightly denser, it would recollapse. Slightly less dense, it would expand forever.
Yes.
So this is the boundary layer.
The boundary. So about 5% of the critical density is in protons and neutrons, what we call baryons. And really, it depends how much dark matter there is. I think the current situation of the community is the following. In the last 10 years, 5 to 10 years, we have witnessed an amazing consensus building up on the existence of dark matter.
Right.
We are left with two problems. One is how much there is exactly.
Yes.
And what is its nature. How much there is exactly is this old question in cosmology of measuring the average density.
Right, whether the universe is at critical density or below the critical density. We don't think it's above the critical density, but but a lot of the direct evidence suggests it's below the critical density.
Yes.
But directly measuring the dark matter, how would we go about determining it? For example, we think we have very good evidence there's dark matter in our own galaxy. How are we going to measure the nature of this dark matter?
Okay, so it depends a little bit what this dark matter is. Now, if it is just ordinary stuff, which is a possibility, actually we should have this nuclear synthesis argument actually tells us that there is probably baryonic dark matter, ordinary stuff which is dark.
Right.
There are not many possibilities which are left. If it was all in gas, we'll probably see it.
That's impossible. We would have detected that a long time ago.
If it's comets, they will evaporate. If it's dust, they will be shining in the infrared. Okay, so basically, we are left with the possibility that there are very small stars which are not bright enough not massive enough to start burning hydrogen.
Right.
What we call machos, massive compact halo objects, or sometimes it's called brown dwarfs.
Right, or maybe just planet-sized objects, like Jupiter-sized objects. It would be very easy to hide a lot of mass in Jupiters in the outer
there are many
galaxy.
Jupiters. Now, we have no idea, of course, how we formed that many small objects, but it is one possibility. Now, it turns out that it is possible to detect those objects, but what we call microlensing.
So this is similar, I understand this is similar to the gravitational lensing that produces the arcs and arclets in clusters of galaxies.
Basically, the idea is that light is bent by gravity. Now, if we look at a star, say in the small galaxies close to ours, the large imaginary cloud, let's look at the star and suppose that one of these objects comes exactly on the light of in the line of sight.
A little star acting as a lens is right in our line of sight. You're
right in the line of sight. What happens is it's too small to block the light of the stars. Actually, it bends the light of the star, and it turns out that the apparent intensity of the star will increase. And since this object is moving, it will start to increase, and then after a while it will decrease. Now, the exciting thing in the last few weeks is that two groups have reported that they have seen events like that.
How do we know this isn't a variable star? Because there are lots of stars that are known to fluctuate in their brightness.
Okay, first we have a very good idea of the shape that we expect, which is
the shape of the brightness curve?
Of the brightness curve. It should be very symmetrical. It has a very specific shape. It also should be exactly the same curve in whatever the wavelength.
That's a good point. So it's the same in the blue and the red, for example.
Yeah. So now, three events is a little difficult to conclude anything from. It could be a new class of variable stars that we don't know about. But when we have tens of 20s of hundreds of events, as we may have in the next few years, we may be able to conclude that at least we have seen this baryonic dark matter.
Now, people have been looking at stars for a long time. How come that people didn't see this before? It's not as though it just started to happen.
This event is has a very low probability. You can actually compute that at any given moment the odds are 5 out of 10 millions.
5 out of 10 million. That's not very high probability.
Okay, so you have to look literally at millions of stars. Until recently, this was not possible technologically. Now, recently, both the fact that we can use computers and the fact that we use a very large electronic camera, the charge-coupled devices, allows us to look at many millions of stars. The group, the American-Australian group who have discovered one of these candidates, have been looking at 10 million stars every night.
Right.
And the French group has been looking at stars on photographic plates, but they have taken literally, I think, 300 photographic plates spaced every few days, and now they are scanning this with modern measuring techniques and put all the data in the computers and reconstruct the intensity of each star.
We should mention something about these CCDs, just for the audience, for anybody, that the CCD recording this session and typical CCDs in camcorders typically have picture elements of about, I think, was 500 by 300, something of that order, whereas this camera that's being used for these experiments has 4,000 by 4,000 picture elements.
Yes,
all of them much more sensitive than the others as well. So it's really an amazing device. It's quite stunning.
So you have 16 million pixels, and actually this camera we are measuring is double, because we are measuring in the red and in the blue. So simultaneously.
So 32 million pixels all at once.
So every time that you read this camera, you basically feel you have 64 megabytes. You feel the hard disk of your computer.
Every 5 minutes.
Every 5 minutes.
That's a fair amount of data. I don't think that my little PC is going to handle that.
Yes,
you may need a little more computing power.
Yes.
Well, that's clearly something that is only going to be as good as the technology, and it is amazing. Another demonstration of how science advances in conjunction with the advance of technology.
So it's too early to say. We need many more events before we can conclude, but there are some hints that we may have found one type of dark matter. Now, we may not have solved our problems totally, especially if the density of the universe, the average density of the universe, is much greater than a few percent.
Right.
Because then we know that there should be something else. And we have a number of other indications, indirect indications in cosmology.
Now, I know your own research is involved in an experimental effort to try to detect the dark matter in the other form of this, what the so-called WIMPs, as opposed to machos, where we could maybe imagine the dark matter in the form of weakly interacting massive particles. Maybe you could tell me a little bit about how progress is developing in that experiment.
Okay, first I can tell you a little bit where this idea is coming from. The basic idea is that if the density in the universe is much larger than 5% of the critical density, then the dark matter cannot be just ordinary stuff. It has to be something else. And a very natural idea is that these particles, is made of particles which were produced in the early universe. The universe was very hot, and you will produce a lot of particles and antiparticles all the time. And somehow these particles manage to stay around. Now, there is a very interesting coincidence, is that if you compute what are the characteristics of these particles, the interaction rates of these particles, if you want them to give you a density of the order of the critical density in the universe today, you come up with an answer which is very specific in terms of scale. It seems to indicate that the scale of the weak interactions, the scale of the physics at where these intermediate vector bosons that particle physicists are interested in, the W and the Z that were discovered about 10 years ago, play an important role. As if this physics was also responsible for dark matter.
Right. So somehow what you're saying is that the very largest scale structures in the universe, the whole notion of cosmology is dominated and controlled by some considerations of particle physics of the incredibly microscopic scale and very high energy.
Very high energy. And that's a very interesting relationship between the very small and the very large.
Right.
And that's somewhat natural. The universe was very hot, and physics at a very small scales have to be very important in the hot.
Early enough time. How early of time are we talking about?
Oh, I don't know, 10 to minus 30 seconds.
Well,
so
maybe these things are still around at a microsecond or something late.
Yes, but a very beginning of time.
Right.
Anyway, these weakly interacting massive particles, if they exist, can be detected. That's another interesting aspect.
Can be detected in the laboratory.
In laboratory. So the basic idea, the density today is related to their interaction properties and the interaction rate, and you can compute the amount of interactions in the laboratory. These particles, if this picture is correct, we have billions of these particles coming through each of us every second.
And it mostly just passed right through.
It passed right through. It passed right through the Earth. Usually, we don't know. But sometimes there would be a small interaction. So
how would you know? What would be the signature of an interaction?
A small deposition of energy. And
inside of a you make a well-shielded crystal.
Yes, you have to have very well shielded. You have to defend ourselves against any radioactivity. So you have probably to go underground,
deep underground,
because of the cosmic rays and so on. And then you will see a small deposit of energy, a very feeble deposit of energy. Now, one of the problems is how do you detect that? So you need sensitivity, but you also need a good enough technology to be sure that this is related to one of these particles passing by and not by just a decay of a radioactive nuclei, a nucleus close by. So we need a lot of redundancy. That is, we need to measure a lot of characteristics of the events. Now, we have been trying to start this with existing detectors, and there have been limits put on. But now we are trying to develop new forms of detectors which take into account very detailed characteristics of interactions.
So they'll discriminate between the cosmic events that you're interested in versus background noise that you'd like to.
That's basically the idea. So the exciting thing is that these technologies now are starting to work, and that we are putting together experiments, and in a year time we hope to begin to get results. So
now here's an example where curiosity-driven research is driving technology.
Yeah. And this technology,
it's not the other way around.
It's not the other way around. And this technology could have a lot of very interesting potential applications in industry and in medical imaging. And actually, we receive a number of inquiries now from industry saying, tell us a little more about that.
It's quite fascinating to imagine doing cosmological research in the deep mine.
Yes. So yes, astronomy
well shielded from all radiation.
Yes.
But I guess that is the nature of it. Well, you know, these direct detection experiments, both of the machos and the WIMPs, are fascinating. But there are, on the larger scale, in the sort of the research that I've been involved in, there is continued progress on measurements of dark matter, not by experimental means, but by observational means of trying to track the dynamics of galaxies and clusters of galaxies. And we are making steady progress in our understanding of how much dark matter might be out there. Because we know in our own galaxy we're never going to see enough dark matter to make a convincing case that the universe is closed or open. I think we're going to have to depend on measurements of the dark matter as you're doing, plus these other experiments.
So I know that you are interested in these velocity flows, and what can you...
Well, the velocity flows are an interesting business. In the last decade, we've determined, because technologies again made it possible, we have taken redshifts of thousands of galaxies to get three-dimensional maps of the galaxy distribution. The redshift of an object is, as you know, proportional to its velocity, at least to lowest order. And because of the nature of the expanding universe, the velocity of a receding galaxy is proportional to its distance. So by measuring redshifts of many objects, we measure their distances, roughly.
But you see some
And,
deviations.
well, deviations are the next order effect, but the lowest order we see maps of the galaxy distribution in space, and we see strong clusters. The galaxy distribution, we've learned, is very far from being homogeneous and isotropic. It's very irregular.
So you have bubbles and filaments
clusters and filaments and voids. It's all a very fascinating topological spongy structure that makes for fancy names like the Great Wall that stretches 500 million light years, or the void in Bootes, or other names.
What is the size of these bubbles?
Well, the typical bubble is 30 megaparsecs, which is about 100 million light years across. That's the typical bubble size characteristic.
And how many depth in bubbles have we seen?
Oh, well, in certain lines of sight we've seen quite a few, but in a typical
2, 3,
line
4.
of sight, in some lines of sight we've seen 10 or 20, but those are very special needles that have been probed deeply. In terms of wide field surveys, the type I've been involved in, we've seen 4 or 5 bubbles, maybe 3 or 4 bubbles along each direction. So we're getting a better and better feel for the nature of the clustering around us, and we've come to realize that the galaxy distribution itself is only the froth. It's possibly not tracing the mass of the universe, but the galaxies may be slightly more clustered than the ordinary mass. But one of the things that's happened in the last few years, and is still fairly primitive but rapidly improving, is the idea that astronomers are developing techniques for measuring distances independent of the redshift by measuring the absolute characteristics of a galaxy. For example, we know that more massive galaxies rotate more rapidly. So if you look at the rotational velocity of a galaxy and compare that to its apparent brightness, you can make an estimate of its absolute brightness independent of knowledge of its redshift.
Yep.
When you compare the two, you start to learn about effects that are deviations from Hubble expansion.
Yes, so it's a deviation from this uniform expansion of the universe.
There's first the uniform expansion, and then there are small deviations from it. Well, what's causing these deviations is a question of great current interest in astrophysical research.
So we see velocities of 600 kilometers per second,
well,
1,000
right.
kilometers
We're
per second.
We're seeing characteristic velocities of 600 to a few hundreds of 1,000 kilometers a second in some cases on characteristically fairly large scales. Now, the most secure number that we've measured in this business is the well-known anisotropy of the microwave background radiation. We know that there's the primeval fireball shining at us from all directions, and only an observer sitting at rest relative to the expanding universe will see this radiation to be the same in all directions. When we look, we see that in one side of the sky it's a little bit hotter than the other side of the sky, and that the deviation from one side to the other is about 1 part in 1,000. Small effect to be sure.
But this means that we are moving.
It means that we're moving, and we're moving. When you go through the numbers, it turns out that our galaxy and the region around it is moving at 600 kilometers a second.
So the current interpretation is that we are falling towards something which is very heavy and is attracting us.
That's right. And so here is where the interconnection of the velocity fields with the redshift survey maps comes together, because the redshift survey maps give us estimates of the density of galaxies all around us. The velocity maps give us indications of how much these lumps and bumps in space might have caused the material to accelerate and move off the co-moving frame. The fact that they are attracting and causing deviations from smooth expansion is all part of what's known as the gravitational instability picture, which is what we think is responsible for the formation of all structure in the universe, galaxies and clusters of galaxies and superclusters of galaxies. And once a galaxy forms in small pieces, then presumably it fragments in some way to make stars and planets. But we see on very large scale, we see that the process is still not complete. That structure is forming, and is in a dynamic state of growing in fluctuation amplitude.
So what is your best estimate for the density? This is somewhat sensitive to the density.
It's a measure of the density, because if the galaxies have no mass associated with them, then they will have no effect. That the smooth expansion will dominate and there will be no peculiar velocities. Yet there are large peculiar velocities.
So this is one clear indication that the universe is very dense indeed.
That seems to be the best evidence that we have that in fact it's not unreasonable to conjecture that the data seems to support an ambiguous interpretation right now. The data is not good enough to be definitive, but there is evidence that is reasonable to suggest that there's enough density in the universe, as indicated by these large-scale flows, to give closure density, which is an amazing idea.
And the reason why we are so interested with this concept of critical density is coming from general relativity. Critical density means that the universe is flat, especially.
Right.
Now, we know since Einstein that any universe which is somewhat curved, either because it's underdense or overdense compared to this critical density, will curve very rapidly.
To get more curved.
Will become more curved very rapidly with time.
Right.
And so there is this basic mystery why we are observing a universe which is so close to be flat, unless it's really flat.
Unless it is really flat, because it would not be this close as it is. It's at least the best evidence is that there's enough dark matter in the universe to make up at least 20% of the critical density.
Yes.
That already says it's more than we're comfortable with in the nucleosynthesis arguments.
So it means that it is probably...
And a factor of 5 from critical, and maybe that factor of 5 is out there in ways that we haven't seen. And some evidence suggests we have seen it. But it's still an evolving story. I think we don't really understand details in any... If you push us very hard in any details, you rapidly find there are gaps.
Yeah, and there are many loopholes in our arguments, and this is fascinating that we still don't understand what corresponds to 90% of the stuff in the universe.
I think we've made progress, but the coming decades will hopefully allow us to make more progress. Yeah. Bernard, it's been great talking with you. I hope we get together again soon, and maybe can continue our progress.
Of course.